Okay, so finally I want to go into some fairly advanced texture mapping stuff here. So I want to kind of go back into the mesh model, find a way to build a UV map on top of a mesh I already have. So we're basically going to have to be able to tell the loader what we want to do. And set up some kind of UV map here alongside. So if we go into the mesh class here we have the float buffer vertices, normals, and we want to add a float buffer for just UV buffer. And again we can say UV buffer equals null. So we probably don't want to always read this, so we can say string file name here and build spherical UV map would be a boolean, just to tell us whether we want to do that or not. So if we don't want to build a spherical UV map, we can probably just, let's go through this where we're setting, okay, we're building these new mesh parts, we're reading not in nodes, somewhere here we have meshes. Just have to make sure that we can actually build that just afterwards. Say, okay, before we return this, before we return the model, let's just say for model dot meshes, perhaps actually for mesh in model dot meshes, that should work. So for each of these we want to build a UV map. Mesh dot UV buffer, should say equals spherical UV map, and we do something else. But if we're not supposed to do that, we just use this. And then we have to say mesh. So we're not wasting any extra memory, we're just setting the pointer to something else, but we have to make sure that we say the mesh also has boolean uses texture, so I'll set that to false in the beginning. So uses texture equals false beginning. In this case, just make sure. So in this case we set it to true, and then we have to go ahead and actually build the UV map. I'm wondering if we should do that inside the model. Or inside the mesh. Yeah, we should probably put this in here. So we could actually go ahead instead and say the mesh will have a function here, like build spherical UV map. We'll just build it on itself, so that's probably our best place to keep this. And that means the model loader should just put this if outside here, like so. If we want to build Spherical UV Map, we'll do it for each mesh. We'll just say build. Okay, so we'll just call this function on the mesh if we're meant to do this. So in the mesh itself, we have the best access to the data here. So we just gotta hope that this isn't called unless these things actually have values. We can put if sentence there to make sure they're not null. But what we're going to want to do here, so we have access to vertices dot capacity, which will hopefully be the correct number here for the number of for the number of vertices. So we can say UV buffer would be vertices.capacity times 2 divided by 3, I guess. I wonder if we can allow ourselves to do this. And then we have to do the whole thing. Actually, I think we can just do this in integer space. It should always work out like this. So we're going to build this buffer. And this is going to be its size, since the vertex buffer has 3 numbers per vertex. This one has 2. And then we need to go through each vertex, and based on its location, relative to the center of this particular object, we need to figure out what its UV coordinate will be. The float buffer here. So, do we have any vertex count here? No, don't really. Where do we build the size of the vertices themselves? Okay, we get this array here, and we know its length. Okay, that's where we get the vertex count from. So we should simply be able to say here int vertex count equals vertices.capacity divided by 3. So we should here be able to say vertex count say for int vertex number starting at 0, vertex number is less than vertex count. So for each vertex we want to make a vector. So vector 3D vertex direction. Let's just call it V to make everything a bit clearer. It's the direction from the center to the vertex. So vector 3D V equals, and since we imagine that the center is just 0, 0, 0 in this context, it's just a vector with the same coordinates as the vertex that we're looking at. So that will be vertices dot get at vertex num. Okay, this will be new vector 3D. Vertices get vertex num. And then the same thing here. Except the index vertex num plus 1 and plus 2. Okay, so now we have our vector. And it should be this vector 3D. So now we have our vector, and this basically tells us the relation of the vertex compared to or relative to the center. And we're simply going to try to figure out where on the surface of a sphere this vector would be pointing to, and say that is the point on a spherical UV map that we want to map to this vertex. Even though it's an irregular object that we're using, we're imagining that we take a big sphere and then kind of shrink wrap our irregular object into that sphere. So vertices get vertex num plus 1, get vertex 1 num plus 2. So we're imagining that we have, vertex num times 3. This has to be like so. Okay, so we're taking every third vertex and then the next one and the next one. And so when we get to vertex num 1 higher, we'll get to the next one after that. So we're taking 3 and 3 numbers together here. Fair enough. So we've grabbed our vector which points to this, now points to the part of the sphere that we're looking at. So what we need to do is we need to find two angles. The angle that this is pointing to in the latitude of the sphere that's surrounding it, and the angle in the longitude. So let's start with how we're going kind of around the globe, as if we're going along the equator. Let's imagine that. So in that case, I'm going to say, I'm going to make a new vector, vector 3D. So this is the vector V. We kind of want the horizontal V. So let's call that VH for V horizontal, which basically means that we're going to drop the Y coordinates and only look at the X and Z coordinates. Equals new vector 3D Vx 0 Vz. So that's one vector. So I have the vector V itself, I have this vector, and finally I'm going to just make a specific vector here for this. Vector 3D, let's it's basically the x-axis or the x vector. Let's just call it, no, we can't call it x, that would be confusing. Let's call it x-axis, xa for that. X-axis equals new vector 3D. So the basic idea here, 1, 0, 0, is that the angle between V itself and this horizontal V will give us the longitude angle, which will be kind of the y coordinates or the v coordinates of the UV mapping, so the second coordinates. That's the angle between the actual vector and its horizontal counterpart. The angle between its horizontal counterpart and the x-axis will be the angle, how far along we are in going along the equator, circumferring, or going around the globe. So that'll be our latitude. No, that'll be our longitude vector. The other one will be our latitude. Anyway, so the first thing we're going to look at, basically the first coordinates, the x-coordinates, so to speak, will be found from the angle between these vectors. So we know how to find the cosine between those angles. We can say BH dot the x-axis divided by BH dot length times the x-axis dot length. Okay, we know that length is 1. We already have it here. We've built it with length 1. So we can say, oh, never mind. So, so now we say the cosine of this angle, if we simply take this like so, let's say math dot a cos, which basically give us the angle given this particular cosine. Okay, so here we have something that gives us the cosine, the dot product between them divided by their lengths. That a cos will give us the angle, so we can call this the latitude angle, or just the latitude. So float latitude equals this, or float of this. Okay, so now we have the latitude, except we have it in the latitude in radians. So now we need to find a way to take that latitude, which should go from basically 0 to 360 degrees, and we need to find a way to distribute that to a number from 0 to 1. But also because the cosine, or the cosine is the same of, for instance, 30 degrees and minus 30 degrees, or 30 degrees and 330 degrees. So we have to find a way to differentiate between them. So we have the latitude here. We can actually go ahead and say if vh.z is bigger than 0, okay, we can start by saying here float latitude. So if it's bigger than 0, then we say latitude equals this. If not, however, if we're at the other side, latitude equals this. start at 0, we go positively up to pi, or 180 degrees. Once we're at the other side, we basically start going down again. We're down again to 0. So what we want to do is we want to say, instead of that being the angle itself, so if we're at 180 degrees, if we're at 190 degrees, we're going to get 170 degrees. So we want to get 180 degrees plus 180 degrees minus the angle. Okay, so basically 360 degrees minus the angle. So this is the angle we get. What we want to say, 2 times math.pi you can say 2.0 times this. You can have this inside, this doesn't matter, minus this angle. So if z is bigger than 1, we get the angle, otherwise we get the negative angle. It doesn't really matter whether it'll just be the other circle around. So we can switch this from less than to greater than, or from greater than to less than, and it'll simply go the other way around, or it should. So now we have the latitude, except the latitude is in radians. So what we really want is the float. No, we don't need float. Now we actually want to say UV buffer dot put, and we want to put a float into a particular index. So the index will be vertex num times 2, because that's where we're at the vertex, and the number will be latitude, which is a number from 0 to 2 pi, so from 0 to 360 degrees, and we need to divide that by pi, basically, actually by 2 pi. 2 times this. This will be inside like so. Okay, so into this part of the UV buffer we need to put this number, which should be a number between 0 and 1. Since the latitude is somewhere between 0 and this number, dividing it by this number should give us a number between 0 and 1. Okay, now let's do more or less the same thing for the longitude. Alright, longitude, except now we're wondering if v dot y is bigger than 0, then we're above the equator, north of the equator, otherwise we're south of the equator. So longitude will be, we take v dot ph divided by v dot length times vh dot length. So we have to divide by both of them now. Okay, let's take this out, because this will only be, this should only ever be between 0 and 90 degrees, so 0 and pi half. But if y is bigger than 0, this is the number, or actually, okay, if it's below y, we kind of want to start at 0. Otherwise, we're going to have to, we either want to start at 0 at the bottom and go up, or we have to have a negative number below, and then we have to basically figure out the going from 0 to 1 here. But let's make it go from 0. So this one will actually be this here plus pi half. So we're going from 0 to 90 degrees, but we actually want that to be from 90 to 180. And when we're going from minus 90 to 0, we want that to be from 0 to 90. So here we're going to be say plus math.pi divided by 2. Okay, so I'm going to take this angle and we're going to add this to it. In the other case though, we're going to have to take pi half first and say, okay, we're going below. So if I get minus 90, I want it to be 0. So minus 90 plus 90 degrees will give me 0. As soon as I'm doing this plus, but this will always give me a positive angle. So yeah, minus this. I have this angle, and I say it's actually 90 degrees minus that angle that I get, which means that as soon as I'm at minus 90 degrees, that's the same cosine as a plus 90 degrees. That'll mean 90 degrees minus 90 degrees, and that should put us at 0. Anything lower will start moving up towards 90 degrees until the y-coordinate is at the other side, and then we're going from 90 degrees and up to 180. So here we're going from, yes, here we have to do the same thing, except we don't need to multiply by 2. And this will be put into this plus 1, and this is the longitude. This is pretty crazy. So now we imagine that we've loaded this UV buffer with this spherical mapping. Now I need to do something with it. So build spherical UV map, then I want to go ahead and say finally uses textures equals true. So the model loader in the end here asked it to build a UV map. And that makes uses textures on the mesh equal true. Then we go to mesh model where we're actually drawing this. And then we take this. Just take this entire thing and move it. And then say if mesh dot part dot mesh dot uses texture, and we do something. Otherwise we do this. mesh.UV buffer. Okay, so now we should be setting the UV buffer into the texture coordinates. And let's allow this texture. Yes, let's import this. Set that there. Set diffuse texture here should do all the work, right? Bind it and everything. So now I'm setting the diffuse texture, but whether or not I'm setting the diffuse texture, I'm setting some coordinates here just to make sure that it doesn't crash. So now I'll be getting errors probably here, where I'm not calling this with any texture. Let's just try to go for true. Let's draw a model instead of a solid sphere. Just going to allow myself to put null here. Take this out for a while and see how this looks. So this is our sphere. Well, the loading didn't crash, so that's something. Now we want that same spherical map to be mapped onto an object, and well, let's just see it for this first. Should actually be mapped individually onto each. Well, something happened. It's not exactly what we expected. We're missing some parts of it. But it is mapping. It seems to be mapping more or less correctly. Except maybe close to the poles it becomes weird. Now, it mapped each part individually, each mesh individually. So it's kind of missing the ends here. There's something not mapping correctly there. Let's try now to change this here to test blob instead. Okay, so here we have this blob. Yes, this part is weird, but the entire thing is texture mapped. This is probably the top of it, and this is the other pole. It actually looks nice on this pole, but just like the sphere, pole on the other side is kind of weird. I don't know if we can blame the texture, if it's the mapping that's weird, but very nice. Mostly is it? Oh, there's something weird going on here. So not everything is correct, but the idea seems to be working. So this is what this looks like now. There are obviously some errors here, but we'll just look through what these are. So we can see if we go around here that kind of the equator of this is giving weird results. And also if we go up top, the poles, the North Pole here and the South Pole here are looking weird. So there are explanations for this. Mainly that if we look into the mesh again here, I've changed some things here, like I'm normalizing beforehand rather than dividing by the lengths, but none of this has any effect. It's the exact same functionality as we had before. So one of the things that is happening, what's happening at the equator, is simply that when v dot y is exactly 0, that means that the vector is already horizontal. So we're getting values right at the horizon, not right at the equator. We're not getting kind of correct value. So what I expected to get was just exactly 90 degrees from these things here. If it was exactly 0, but that wasn't the case. So I added this if sentence here, just saying if y is exactly 0, I'm just going to put this to pi halved, or 90 degrees. And I added stuff here that I don't think actually matters at all. The h, I think we can simply take this entire thing out. This didn't really fix anything. Let's look at this. You can see that the equator is fixed now. But the poles are still weird. North Pole and the South Pole of all of these objects, both the smaller spheres and the big one. So this here didn't really matter at all. So it looks like this now. We're just adding an if here. If it's exactly 0, we do this. If it's bigger than 0, we do this. Otherwise this. We're splitting this up into separate parts. The other thing, however, is that it's possible. Well, this is not something that's common, so let's not worry about that. But this is. So if we have an exactly vertical v, which means we have coordinates that are exactly on the North Pole or the South Pole, then obviously making this horizontal, where we basically say Vx 0 Vz, if Vx and Vz are already 0, now we have vector 0 0 0. So taking the length of that or dividing by that, it'll just give us Arrhenius results. And so by checking if the length is 0, we're just going to fix the x of it to 1 just to get some result. It fixes the poles in that you don't get this weird, like absolutely strange results. Instead we get something and it hangs together on the textures. But if we look here and draw a little bit, oops, in here, so if a texture is here, and we imagine a sphere here that we're texture mapping, so it looks like this. If we have some vector here to a point in our model that would be here in the sphere map, this is okay. So this will map this point and this point and this point all around. Will map to these points here, which is fine. As soon as we go right up to the top, if we make the sphere and UV map at the same time, we'll actually do multiple kind of definitions of this vertex here rather than just having the one vertex. And so we'll have these different top coordinates on that. However, when we're sphere mapping it afterwards, we're always going to get the same result here, meaning that we'll probably always get either this corner or this corner, but it doesn't matter which one. If we always have this one, rather than mapping this area here, this area here, this area here, getting some kind of even distribution over this, instead we're going to end up mapping triangle here, triangle here, triangle here, triangle here, always mapping to the same coordinate there. So we're going to get a pretty wonky top there. What it did as well was I made this little image. You can just look at it here. This image here, just to kind of see where the North Pole is, what's the South Pole, how the equator looks, and just see the colors, that everything is kind of distributing correctly. And when I set that up, which is called sphere map test.png, you can see what it looked like before we changed these things. It was kind of easier to see using that image, kind of easier to see exactly where these errors were happening. So along the equator here, and then the poles here, kind of cutting this. as soon as we set this here straight, all of this one is probably not coming into effect, but let's leave it there anyway. If v length is 0, we just put it straight up. Then we can see that the equator is fairly nice on this side. I'll show you the last artifact that we have later. And we go up here, and we can see that it's a bit off. It's a bit weird, but at least it's mapping to something. The same thing if we go down below. At least we can see this is the South Pole, the other one is the North Pole, and we have some mapping of this image, but the very end still gets a little bit weird. The last final artifact that we have is if we go here, you can see right here suddenly something weird is happening. It's happening on every single one of them. You can see it very nicely here. And what's happening there is simply that if we imagine that we're setting coordinates here, so a vertex here will get the coordinates, let's say here, a vertex here will get coordinates here, a vertex here, get coordinates here, so on and so forth, until we come all the way around. Then this vertex will get these coordinates, this vertex get these coordinates, and then suddenly we're going to be making polygons here between this vertex, or these vertices, which have values here, and these vertices, which have values here. And OpenGL just isn't clever enough on its own to realize that then it should be mapping around to here. Instead, it just maps from here, or from here to here, just mirroring it all the way back. And so if we go in here, we can see we go take the whole image all the way around, and then suddenly here in one go we just mirror the whole thing back. The way to fix this would be to actually map this entire edge, that is these coordinates here, to actually map them twice, or basically set up these vertices twice and have one set of them with these coordinates and the other set with these coordinates. And that's what we actually do when we build the sphere ourselves. But here we're mapping this afterwards, we're mapping it onto a model that has already been made. So you could actually go through it, set up some structure and kind of copy those vertices and have different UV coordinates on the vertices depending on in which polygons they are. Then you have to go through the entire index list and figure out which parts they are. You could do this and then just add that to the UV list. But for now, we're going to allow that artifact to stay. So we have the full mapping now. We have this artifact here on the end, and the poles are also a little bit wonky, but I'm going to allow that to stand. If anybody wants to go and actually figure out how to fix this and do this better, you're welcome to, but I think it would be a better use of your time to actually just build UV maps in a 3D kind of modeling studio and just spend your time reading the binary format that saves into your file and building a better UV map rather than doing it in code yourself. But this is a nice way to kind of understand these maps. This is the spherical map. The difference between a spherical map and a cylindrical map is that while the spherical map, I was closing one note, that while the spherical map imagines that we are kind of taking these two angles, the angle around and the angle around the equator and the angle up and down the longitude. A spherical map would say the second coordinate will just take, so if this is my irregular model, I'll just say the highest y value and the lowest y value will become 0 and 1 in the second coordinate, and I'm only going to take the kind of around the equator angle. So I'll always do the same thing. I'll take this vector, I'll take the x and z coordinates of it, and I'll do the around the equator angle in the same way. But rather than doing an angle here, imagining that I'm wrapping around, I will just take the y coordinates and I'll stretch them. I'll find the lowest and the highest and say this one will be mapped to 0, this will be mapped to 1, and everything else in between. And so we end up with something that we can imagine is like a texture in a cylinder. And rather than what we did before, where we said we have this irregular object and then we kind of shrink wrap this sphere all the way around it, instead we say we have this cylinder and we're just shrink wrapping horizontally. We're not shrink wrapping all the way around. Otherwise it's the same. So we do the x coordinate or the u coordinate of the UV texture the same. The v coordinate would simply be the y coordinates clamped down to between 0 and 1. So if we look at this again here, just do the moon texture again. This looks like so on this model. And the original model that we're going to do here, we're obviously mapping each of these at a time. This looks weird. We would want to have the texture image part of the material. So the material says this is the texture you should read and this is the texture you should read. Right now we're just reading one texture and putting it on the whole thing. It's no problem to take this model file here and saying this file here, we just add part of the material here. We have textures, so we could say, you know, we could add something. We could just look at the definition of this and basically set the actual texture, set the image, and then we have a mapping now. The only thing we need is to have the material, the texture part of the material, rather than just one big texture. And it'd be no problem for anyone to implement that, actually having the image of the texture inside the material, reading that correctly, and then reading the correct file. However, now we're going to have this moon, but the other thing I'm going to do is I'm going to change this to test blob. See what that looks like. Okay, so this is pretty nice. We have these artifacts here, but if we look at the three-dimensional image here, we can see why this is. It's simply because it's so irregular, this object, that the surface kind of gets this. These polygons here are kind of almost parallel with a vector straight out of the center and out of this. So this kind of gets stretched there just because of the shape of this. If we go up to the pole here, see there's probably some wonkiness here, but with a texture like this it's not as obvious. This artifact, however, is still here. And we can see this is where it just wraps around and mirrors itself all the way back, the entire texture, over a single line of polygons. There's nothing I'm going to do now to fix this, but you can figure out ways, and you can also just have higher poly models or have the textures so that they will not look too bad when this happens. So this is what this looks like. If we take the model we made earlier, which I think called blob 2, let's just see how this wrap, because putting a cylindrical map, a spherical map around a cylinder, especially when the cylinder lies on its side, is kind of weird. So this looks nice on this side. This looks very strange on this. The sphere, however, here texture maps really nicely, except maybe the poles. Yeah, this is kind of weird here on the pole and there. So there are artifacts, but this is working, and we're doing texture mapping and gaining a better understanding of that entire thing.